Have you ever wished you could design custom hardware, maybe for a really specific task, with the same kind of ease and speed you write software?
Mm-hmm.
Imagine taking your algorithms, maybe written in C or C++, like something familiar, and having them just automatically transformed into high-performance hardware.
Yeah, that's the dream for a lot of people.
Well, today, we're doing a deep dive into high-level synthesis, or HLS. It's a technology that's, well, actually making that vision a reality.
It really is. It's a critical bridge, fundamentally reshaping how we develop these complex electronic systems.
Okay, let's unpack this.
Right. So our mission for this deep dive is to really explore HLS. What are its core principles? What are the big advantages? Speeding up design, making hardware development more accessible.
And the challenges, too, I assume.
Oh, definitely. And the challenges it still presents.
Yeah.
We'll look at how it's driving innovation, especially in hot areas like AI acceleration, signal processing, and where it seems to be heading in the future.
Okay, so at its heart, HLS is basically translating software into hardware, right?
Okay. Pretty much, yeah.
It takes these high-level languages, C, C++, System C, and automatically turns them into hardware descriptions, usually in things like Verilog or VHDL.
Exactly. Those are the standard hardware description languages, HDLs.
So engineers can work higher up, more abstractly, but still get those, amazing performance benefits you only get with custom hardware.
Precisely. The whole point of HLS is to hide or abstract away the really intricate details of traditional hardware design, what we call register transfer level or RTL design.
Okay.
You can literally think of it as converting software-like code straight into a hardware circuit description. Now, the idea itself isn't brand new.
Right. I heard it goes back a bit.
Yeah, early tools popped up in the 80s, believe it or not. But
Yeah.
HLS has really matured now. It's a mainstream part of designing systems on chip, SoC6. Those single chips that have everything on them.
So why now? Why is this bridge so crucial today? What's a big problem HLS is solving right now?
It really boils down to complexity. Modern digital systems are just getting incredibly complex. Doing manual RTL design is low level, it's easy to make mistakes, and it just takes an extraordinary amount of time.
Painfully slow sometimes, I bet.
Oh, yeah. HLS tackles this directly by raising that abstraction level. It's this abstraction productivity paradox in hardware design. We saw the same thing happen in software, right?
Yeah, moving from assembly to higher level languages.
Exactly. Huge productivity gains. It's not just about being more efficient anymore. It's almost a necessity to handle the sheer scale and complexity of today's designs.
And it sounds like it's not just helping traditional hardware folks. It's opening doors for others, too.
It absolutely is. HLS is a huge enabler for what we call domain-specific accelerators, or DSAs.
Okay, DSAs.
These are very specialized, very computation-heavy components. You see them a lot in AI, machine learning, digital signal processing, places where general-purpose CPUs just don't cut it.
Right, they'd be too slow or inefficient.
Exactly. And here's the key thing. Often, the algorithms for these DSAs are developed by data scientists, algorithm engineers, people who are brilliant with C++, but maybe don't have that deep traditional hardware design background.
I see. So HLS bridges that gap.
Perfectly. It bridges that interdisciplinary divide. It empowers those algorithm developers to directly influence the hardware implementation that really speeds up creating these highly optimized custom solutions.
Okay, so let's get into the nuts and bolts. If I say, give an HLS tool my C++ code, what actually happens? How does it magically become a circuit? What's that deep dive into hardware actually look like?
Right, it's not quite magic, but it is a defined flow. Typically, it starts with what we call high-level design entry. That's just you writing your algorithm in C, C++A, or maybe System C.
Okay, step one.
The code. Step one. Then comes behavioral synthesis. This is where the HLS tool automatically creates an abstract hardware model from your code. It captures the behavior you intended.
An abstract model.
Okay. Then, finally, there's RTL generation. The tool spits out the actual hardware description, the Verilog or VHDL code, and that code then feeds into the standard hardware design steps like logic synthesis, place, and route.
The usual stuff.
The usual stuff. And critically, running all through this is verification. You have to constantly check that everything is correct.
That sounds almost too easy.
Uh-huh.
How does it know what kind of hardware to make? Does it just guess?
Haha, not quite guessing.
Yeah.
Inside that behavioral synthesis step, the HLS tool does three really fundamental things. First is scheduling.
Scheduling.
Yeah, figuring out the optimal timing, which operations happen in which clock cycle to make things fast and efficient.
Okay, timing. Makes sense.
Second is allocation. This is where it assigns those operations to the actual hardware resources available, things like ALUs for math, registers for quick storage, memory blocks.
Got it. Assigning jobs to the hardware bits.
Exactly. And the third is binding. This maps the specific instructions and variables from your C++ code directly onto those hardware components it just allocated.
Wow. So it's basically automating the microarchitecture design. It figures out the internal structure.
That's a good way to put it.
I mean, I just write my code, hit a button, and voila, perfect, super efficient hardware. Is it that simple?
That raises a really important point. While HLS tools do automatically create that cycle-by-cycle detail for the hardware,
Yeah.
and they can generate lots of different microarchitectures to explore trade-offs, speed versus how much hardware area it takes up. It's definitely not a magic button. The core task here, mapping that high-level behavior to hardware, is actually what we call an NP-hard problem.
Uh-oh. NP-hard sounds hard.
It means it gets incredibly complex, incredibly quickly. Finding the absolute perfect solution is often computationally infeasible for large designs. So the designers, the humans, still need to provide guidance.
How do they do that?
Usually through special comments or directives in the code, often called pragmas.
Pragmas.
Think of them as high-level architectural hints. You're guiding the tool, saying, hey, try to optimize for performance here, or try to minimize power consumption for this part. You're steering it towards the kind of solution you need.
I see. So HLS changes the job. It's less about writing low-level RTL code
Right.
and more about thinking at a higher architectural level and giving the tool the right hints. Strategic guidance?
Precisely. It transforms the nature of hardware expertise.
Okay, so HLS is clearly a game changer, but it sounds like it's not all smooth sailing. What are some of the hurdles or complexities designers run into?
Well, one primary challenge is what we call abstraction limits, meaning not everything translates easily or efficiently from a high-level language. If your algorithm needs really fine-grained, low-level control over hardware signals or complex dynamic memory stuff.
Like pointers doing complicated things.
Yeah, exactly. Sometimes, for those specific cases, sticking with traditional RTL design might actually be better or necessary.
Okay, so it's not a universal solution for everything.
Not yet, anyway.
And what about performance? Getting the absolute best speed or lowest power. Is that guaranteed?
That's another big one. Achieving optimal quality of results, QRR, we call it that balance of performance, area, power.
Yeah.
That's a significant hurdle.
Why is that so hard?
Because the number of possible microarchitectures you can create just by tweaking those pragmas, it grows exponentially. There are just so many combinations.
The exploration space is huge.
Exactly. Finding the truly optimal configuration in that vast space is really tough. And checking each potential design isn't instant. Evaluating one set of pragmas can take hours. That really slows down the optimization loop.
Which leads to kind of an interesting point, maybe a contradiction. We said HLS democratizes hardware design, makes it more accessible.
Yeah, which it does.
But I've also seen sources say you still need considerable hardware design expertise. How do those two things fit together?
Yeah, that really highlights what we often call the expertise gap. So yes, HLS definitely lowers the barrier to entry for software engineers. The learning curve is less steep than full-on RTL, but to get really high quality of results, to squeeze out that last bit of performance or power efficiency,
You need more.
you still need a deep understanding of how software concepts actually map onto physical hardware. You need to know how to use those pragmas effectively, understanding the implications of each hint you give the tool.
So the basic use is easier, but high-end optimization still requires that hardware background.
Pretty much. That really detailed optimization, figuring out architecture-specific tweaks, that's typically still the domain of experienced hardware programmers. Without that foundation, the tool's automatic stuff might give you something that works, but it might be far from optimal.
Creating a kind of expertise bottleneck.
Exactly. The promise of broad access is there, but it's somewhat limited by the need for these specialized designers who can really speak both software and hardware fluently.
Okay, I can see that. What about finding bugs? Verification debugging. Is that easier or harder with HLS?
That's another area where it's complicated. Bit of both, really.
How so?
On one hand, HLS is often promoted as enabling easier debugging and verification because you're working at the C++ level, which is familiar and faster to simulate.
Right, debugging C++ is generally faster than debugging VHDL or Verilog.
Generally, yes. But after the tool does its synthesis, actually Ensuring correctness and debugging potential issues can be challenging.
Ah, so the challenge shifts.
It does. There's this semantic gap between your original untimed C++ code and the cycle-accurate, highly parallel RTL hardware description the tool generates.
Meaning the translation itself can introduce issues.
Potentially, yes. Bugs can pop up not just from flaws in your original algorithm, but from how the HLS tool interpreted your code, or maybe how different optimization pragmas interacted in unexpected ways.
That sounds tricky to track down.
It can be. It means you need a more layered verification strategy. You need things like CRTL co-simulation, maybe formal verification methods to really make sure the behavior is consistent across those different levels of abstraction.
Okay. Despite these challenges, though, it sounds like there's a pretty healthy ecosystem of HLS tools out there.
Oh, definitely. It's a very active area.
Can you tell us about some of the main players? If someone's looking into this, what tools are they likely to encounter?
Sure. The market has some clear leaders. You've got AMD Vitis HLS, obviously optimized for AMD's FPGAs. Then there's the Intel HLS compiler for Intel FPGAs.
Makes sense, tied to the big FPGA vendors.
Right. But you also have major EDA companies involved. Cadence has Stratus HLS, which targets a pretty wide range of FPGAs and also ASICs custom chips. And Siemens EDA has Catapult HLS, which is often noted for its strengths in low-power optimization and its AI-focused solutions.
Interesting. And are there open source options too?
Yes, there are important ones. Tools like LegUp and Bamboo offer more flexibility, especially for academic research or maybe very specific niche applications. They're definitely part of the ecosystem.
And you mentioned System C earlier. How does that fit in with these tools? Is it required?
Not always required, but System C is pivotal, really important. It's actually an IE standard, IE 1666. It's essentially a set of C++ classes and libraries specifically designed for system-level modeling.
Okay, so it lets you model things before you even get to HLS.
Exactly. It lets designers model really complex systems at a high level of abstraction. You can focus on the essential interactions, the data transactions, without getting bogged down in low-level signal wiggling quite so early.
And the benefit there is?
The big benefit is enabling a verification shift. You can do really detailed, even bit-accurate modeling and thorough verification in System C before you even run HLS.
Ah, catch bugs earlier.
Way earlier. And simulating System C is orders of magnitude faster and cheaper than simulating or debugging the generated RTL code later on. It's a huge time saver.
Okay, that makes a lot of sense. Now, you mentioned pragmas a couple of times as being crucial for guiding the tools. This seems like where the designer really interacts with HLS.
Absolutely.
Can we dive a bit deeper? How exactly do these pragmas help optimize the hardware? What are they actually telling the tool to do?
Right. Pragmas are indispensable. Think of them as architectural constraints you're layering onto your algorithm. They fundamentally change the microarchitecture the HLS tool builds.
So they directly influence the hardware structure.
Directly. They let you specify things like how memory should be organized, how much parallelism the tool should try to find, whether to pipeline operations.
Okay, give me an example. Like, what does a common pragma do?
Sure. A very common one is hashtag pragma HLS unrolla. If you put that on a loop in your C++ code, you're telling the HLS tool, hey, instead of running this loop sequentially, replicate the loop body in hardware so iterations can run in parallel.
Ah, so it physically creates more hardware to do things simultaneously. Faster, but uses more area.
Exactly. That's the trade-off. Another key one is hashtag pragma HLS pipeline. This tells the tool to overlap the execution of loop iterations, like an assembly line.
So as one iteration finishes stage one, the next one starts stage one.
Precisely. It keeps the hardware busy, continuously, dramatically improving throughput, how much data you can process per second.
Very cool. Are there others?
Oh, yeah. There's HLS data flow for creating parallelism between different tasks or functions. HLS array partition lets you split arrays in memory so you can access multiple elements at the same time. And there's also resource sharing, where you tell the tool it's okay to reuse certain hardware components, like maybe an expensive multiplier, for different operations to save area.
Wow, okay, so it's really not just about writing clean C++ code. It's about understanding these hardware concepts, parallelism, pipelining, memory access, and using pragmas to tell the tool what kind of hardware structure you want.
You've nailed it. That's the core skill in effective HLS design.
And you mentioned HLS is a big deal for AI and machine learning accelerators. How do these optimizations play into that specific domain?
That's a great connection, because that's where quantization becomes a co-design opportunity.
Quantization,
Yeah.
meaning using fewer bits for numbers.
Exactly. Many AI and ML algorithms work surprisingly well using lower precision numbers, what we call fixed-point arithmetic, maybe 8-bit integers instead of standard 32-bit floating-point numbers.
And that saves hardware resources.
Massively. Fewer bits means smaller multipliers, smaller adders, less memory bandwidth, lower power consumption. Huge savings in area and power.
Okay. And HLS helps implement that.
It's perfect for it. HLS tools typically have built-in support for arbitrary precision data types, things like a pint for integers or appfix for fixed point numbers, where you can specify exactly how many bits you want.
So you can define an 8-bit integer or a 12-bit fixed point number right there in your C++ code.
Right in the high-level code. This bit-accurate implementation is crucial because it lets you model and simulate the precise effects of using fewer bits like potential overflow or rounding errors directly.
Before you even generate the hardware.
Exactly. You can explore those trade-offs easily, and getting that bit width right can lead to order-of-magnitude improvements in performance and power for specific AI tasks. It's a prime example of HLS enabling fine-tuned hardware tailored to the algorithm.
So bringing it all together, where is HLS making a tangible difference today? What are some key application areas where it's really shining?
Well, we touched on AI accelerators, both in data centers and especially at the edge. That's huge.
Like Edge AI.
Yeah, enabling that low-power, low-latency processing directly on devices. It's also heavily used in FPGA-based acceleration generally for things like software-defined radio or accelerating complex tasks in data centers.
What about other areas?
It's a natural fit for anything involving intensive signal processing. Think image and video processing algorithms for object detection, feature extraction, stereo vision are often accelerated using HLS. Same for digital signal processing, DSP, in communications or audio.
And the common thread seems to be computationally heavy tasks with potential for parallelism.
That's exactly right. ML algorithms, as we discussed, fit that perfectly due to their complexity and inherent parallelism. Custom hardware designed with HLS can often outperform even powerful general-purpose accelerators like GPUs or TPUs by a significant margin, sometimes an order of magnitude or more for specific tasks.
Because it's tailored.
Because it's precisely tailored. And HLS lets data scientists' implementations, their C++ code, be the direct input for that hardware design. You skip that manual error-prone translation step from algorithm spec to RTL.
That seems really powerful. This trend of HLS-driven specialization, it feels like it's changing the landscape.
It absolutely is. It's pushing computing architectures towards being more heterogeneous systems with different kinds of specialized processors working together, more efficient, more domain-specific. And as we said, it's a massive catalyst for Edge AI, enabling intelligence right where the data is generated, which is great for latency, power, and privacy.
Looking ahead then, what's the future trajectory for HLS? Is it just going to keep growing? Is it destined to take over hardware design?
Well, there's definitely a growing consensus in the industry that HLS is poised to eventually replace RTL as the main way we do front-end design.
Really? Replace RTL entirely?
Maybe not entirely overnight, but become the predominant method. It mirrors that historical shift we saw from designing with logic gates to designing with RTL. Abstraction levels tend to rise over time.
But it'll be gradual.
Oh, absolutely gradual.
Yeah.
For the foreseeable future, HLS design blocks will need to live alongside and connect cleanly with existing handcrafted RTL blocks within the same chip. Coexistence is key.
Okay. And thinking back to that expertise gap, the need for deep hardware knowledge to get the best results, what role might AI play here? Could AI help make HLS even more powerful or accessible?
Definitely. That's probably one of the most significant and transformative trends we're seeing right now.
AI helping design hardware.
Yes, specifically the integration of AI and machine learning techniques into the HLS optimization process itself.
How would that work?
The idea is to use ML models to automate things like inserting the right pragmas or tuning the parameters associated with them. Remember that huge exponential search space for the best microarchitecture.
Yeah, the one that's too big for humans to explore fully.
Exactly. AI techniques like reinforcement learning or predictive modeling could potentially explore that space much more effectively and efficiently than a human designer can manually.
So the AI would suggest the best pragmas or configurations.
Precisely. This AI-driven HLS could automatically figure out complex optimization strategies, addressing that bottleneck we talked about. It has the potential to fundamentally change hardware design again.
How so?
By truly democratizing high-performance hardware. If AI can handle more of the complex, low-level optimization decisions, it significantly reduces the need for that scarce, deep hardware expertise. It could unlock new, maybe non-intuitive, but highly efficient architectures that humans might struggle to find on their own.
Wow, that really lowers the barrier significantly.
It could, yeah. It's a very exciting direction.
So wrapping up this deep dive, it seems clear that high-level synthesis has already fundamentally reshaped digital hardware design. It's raised the abstraction level, given us huge productivity gains,
Undeniably.
and it really is bridging that gap between software and hardware, making custom hardware design much more accessible to a wider range of engineers and scientists.
Absolutely. And while challenges definitely still exist, the QR problem, the verification complexities, that expertise gap, the tools are constantly getting better, especially with these emerging AI and ML techniques coming online to help automate optimization.
The demand isn't going away either.
Not at all. The push for more specialized, high-performance, power-efficient hardware, especially for AI and edge computing, just keeps growing. That ensures HLS will play an indispensable role moving forward.
So as HLS continues on this path, likely becoming the dominant way we approach front-end design, really cementing itself as a cornerstone for innovation.
Right. It leads to a final thought, maybe something for you to consider. As this convergence of software and hardware engineering continues, driven by tools like HLS and maybe AI, how might that not only speed up innovation, but fundamentally redefine what we even mean when we say design hardware in the future? What does that role look like in the digital age?